Hello, everyone. Welcome to this really exciting presentation, actually, by Dr. Richard Clark, Global Lead Energy at Morgan Advanced Materials. So this morning we've heard, about the market. We've heard about the electrolytes, about concepts for anode, and now we're actually going to change our focus and look at the often neglected opportunities for cathodes in solid-state batteries. So as usual, the presentation will be around 20 minutes. Dr. Clark, I will let you know 2 minutes before the end of your time. I will give you a heads up. And a note to the audience, as usual, make it as interactive as possible. Type in your questions to the right-hand side. We will ask almost all the questions. And then Dr. Clark will join us in the networking break, and you can follow the discussions with him there. So the stage is yours now, Dr. Clark, and you may start.
Great, thank you, Kasha. So good morning, good afternoon, good evening. I'd like to thank yourself and your team for inviting me to speak today, and I'd like to thank all the listeners for choosing to listen to what I have to say on the subject of opportunities for cathodes in commercialized solid-state batteries. First, going to just say a few words about my company, Morgan Advanced Materials. So we are an English company founded in 1856. We're publicly traded. We've been on the London stock market since 1946. We have 75 global manufacturing and R&D locations, which are pretty much spread between North America, Europe, and Asia. We cover a wide variety of markets, which you can see listed here. We have 5 global business units. Our purpose is to use advanced materials to help make more efficient use of the world's resources and to improve the quality of life. So looking at what's our interest in lithium-ion battery technology, this is obviously a very, very high-level schematic of making lithium-ion batteries. We are the leader in provision of refractories for the furnaces that are used in primarily cathode manufacture. So that's actually a very significant business for us, and you would imagine, of course, that's relatively proportional to the amount of electrode materials being made, and it also gives us an insight as to how the actual production is going globally, away from the market research companies. Second interest in terms of commercial is thermal management materials, which are for prevention or mitigation of propagation of thermal runaway at cell, module, and pack level for energy storage and for electric vehicles. And then a sort of emerging application relates to material recycling, but only for pyrometallurgy, again on the refractory side. Our developments on the liquid electrolyte side, new or modified anode materials, not necessarily the active materials, but other things that go into the mix. On the separator side, there is some work going on related to fibers. We've got some novel fibers which can be used in non-woven separators, which is an emerging category. And then obviously solid state, that's one of the reasons I'm here today. We're doing a lot of work on electrolyte materials, and the area we're focusing on, novel of course, but low-cost processes. And we heard earlier today from Yoel, that is one of the big challenges, is trying to bring costs down, and we are working in that area. Just wanted to say thank you to the Faraday Institution publicly, who we're doing a lot of work with Faraday Institution in the UK. So we are part of the Future CAP program, Professor Serena Cusson at Sheffield, the degradation program, which is Claire Gray at Cambridge, Solbat with Peter Bruce and Mauro Pastor at University of Oxford. And we have 2 funded industry sprints, one with John Irvine's group at the University of St Andrews, also working with Ilika, who you're going to hear from a little bit later, and then Professor Dan Hewitt at University of Southampton, where we're working on some conductive glass materials. Yesterday, we had a super talk from Dr. Kang Xu, talking about the origins of the industry. So I'm not going to overlap too much with him. But there is a paper here which I reference, which I think would be great if you're interested in the history. How do we get where we are? Not just on the anode side. It is important to realise, why we got where we got. So if you think lithium metal, we started with lithium metal. Lithium metal makes a lot of sense, has high specific capacity, a low density, and extremely low electrode potential, which makes it the ideal anode material for high voltage and high energy batteries. Stable against several non-aqueous solvents because of the formation of a passivation film on the lithium surface. But with rechargeable batteries, you have the difficulties with cycle life and safety, essentially related to the formation of dendrites. Hence, you get into intercalation type anodes, for example, graphite, which we're all familiar with,